Hi everyone, today we're going to talk about composite figures. So the first thing we need to talk about is what is a composite figure? Well, a composite figure is a figure that can be split into basic figures, such as circles or rectangles or trapezoids and regular polygons. Pretty much any figure that you can think about, that's what could make up a composite figure. So we find the area of composite figures by finding the areas of the figures that we break the figure into individually. So the areas of all the little shapes that we break it down into, and then subtract or add the individual areas together. So we might be adding the area of a square and a triangle to make the composite figure's area, or we might be subtracting one area out of the other. It just depends on the shape. So in example 1, we want to find the area of the composite figure. But first we want to identify what the composite figure is made up of. What is it composed of? And when you think of composite, maybe you think of composition, maybe you think of like a composite, and it's made up of many different things. So in this shape, what basic figures can we break this into? Well, we can break it into this shape. What is this? That's a rectangle. And then we also have these two kind of semicircles, right? And I noticed that these two semicircles have the same radius. So if there are two semicircles with the same radius, then two semicircles together really make one circle. So I'm going to find the areas of the figures that we broke it up into, so the rectangle and the circle, and then in this one, because the shaded area is everything, then I'm going to add the area of the rectangle and the area of the circle together to get the area of the composite figure. So let's talk about the formulas for the area of a rectangle. The area of a rectangle is the base times the height. And the area of a circle is pi r squared. So all I need to do is find the area of both figures and then add them together. So let's talk about the area of the rectangle first. The base right here is labeled 8 centimeters. The height is not labeled. However, if I take this radius, remember that the radius is the same throughout the whole circle, so if I let it kind of swing down, then this is 2 centimeters. And if I let it kind of swing up, then this is 2 centimeters. So the full height of that rectangle is 4 centimeters. So if I multiply those together, 4 centimeters times 8 centimeters is 32 centimeters squared. Now I'm going to find the area of the circle. Both semicircles added together is one whole circle's area. So whenever I insert into the formula, pi is still pi. The radius in both circles is, or in both semicircles is 2. So I'm going to square 2. 2 squared is 4, so the area of the circle is 4 pi centimeters squared. So if I add those two together, then 32 centimeters squared plus 4 pi centimeters squared, they're not like terms, so I just keep the area of the composite figure as 32 plus 4 pi. I put that in parentheses because both pieces are given the centimeter squared units. And there we go. So that's an example of finding a composite figure's area that's made up of a rectangle and a circle, and adding them together. So let's look down at example 1b. 1b says, find the area of the composite figures. What basic figures can we break this into? Well, the larger figure is a circle, and the interior figure is a polygon. Now we're going to assume for the purposes of today that all of the polygons that we see, unless stated otherwise, are regular. So this is a regular 1, 2, 3, 4, 5, 6 hexagon. Regular hexagon. So let's talk about the formulas for the area of a circle and the area of a regular hexagon. A circle's area, as listed in the previous problem, is pi r squared. And here the radius of the circle is 16 centimeters. So I can go ahead and find the area of my circle. 16 squared is 256. So 256 pi centimeters squared. That's my area for the circle. So now let's talk about the area of a regular hexagon. The area formula of a regular polygon in general is 1/2 times the apothem times the perimeter. So we've got some work to do. So I'm going to look over here. I'm going to draw another radius, which is also 16 centimeters. I'm going to draw the apothem, which is always from the center to the side of the polygon at a right angle. I'm going to find the measure of the central angle, so 360 degrees divided by the number of sides in a hexagon, which is 6. That's a 60-degree angle. So I'm going to take this triangle and I'm going to bring it out, because there are pieces that I need that I don't have to find the area of that whole hexagon. So here's my right angle. Here's my 16 centimeter hypotenuse. This whole central angle measure is 60 degrees, so half of it is 30 degrees. That means that this is 60 degrees over here. So I've got a special right triangle here. My short side is s, my long side is s squared roots of 3, and my hypotenuse is 2s. If 16 equals 2s, then s is 8. So here is 8. My apothem is 8 square roots of 3. And if this piece right here is 8, then this whole side right here would be 16. So my area equals 1/2 times the apothem, 8 square roots of 3, times the perimeter, which is 6 sides times 16 centimeters each. Okay. So half of 8 is 4. 4 times 6 is 24. 24 times 16 is 384. And I still have my square root of 3, and I'm measuring in centimeters squared. So for this problem, because we're trying to find the area of the composite figure, and the composite figure is always going to be the shaded bit right there. So it's not going to be the whole thing, it's going to be the shaded piece. So in order to just get the shaded area, well, I need to find the area of the whole circle, and then I need to subtract out of it all of this blank space. So that regular hexagon. So in this instance, I'm not adding these two areas together, I'm subtracting. I take the bigger area, which is the circle, 256 times pi, and I subtract from it the smaller area, 384 square roots of 3. And I'm still measuring this whole area of the composite in centimeters squared. So this is my area for that composite figure, that shaded area. So let's move on to the next page. Now, problem C is flawed the way that it is. It says, what basic figures can we break this into? And we really don't have a lot of information about this. Typically, I would say that because this problem is flawed, we're going to skip it and we're going to move on because there's not enough information. However, what I'm going to do is give you enough information so that we can use this problem to practice. So I'm going to make sure that we understand that this is a square and this is a square. And by definition, that means that we have 4 right angles here. We have a 16 centimeter side, and then 3 other 16 centimeter sides. And then same situation inside. We have these right angles, and then these may not necessarily be 16 centimeters. However, they are all congruent side lengths. So I'm giving this to you. This was not provided for you. The problem itself was flawed, but if you make these adjustments, then we can make something out of this problem. So it's not implied that you should be able to mark these. In fact, you shouldn't, but I'm telling you that you should mark them right now. So what basic figures can we break this into? Well, we have a larger square, large square, and we have a smaller square. Now it's interesting because we have a large square and a small square, but the only shaded part is the small square. So that tells me that rather than just finding the area of the small square, I should be thinking about how to utilize the information in the big square, because there's not really going to be any subtracting of a square area from a square area. So let's rethink about this. We do have a small square, but instead of talking about this big square, let's talk about maybe some of the pieces that it can be split up into as well. So I notice that I have little triangles. Right? I've got 4 little triangles, and all of these little triangles are congruent to each other. But if I can utilize those small triangles, then perhaps I can find the area of my small square. So let's change this up. Let's say that we have a large square, and then we have 4 triangles. And if I can find the area of the large square and then subtract out the area of the small triangles, then I will have this. Now, of course, I could use my knowledge of regular polygons, but I'd like to go with this route. So my large square, the area of a square, is the side length squared. So for that large square, the side length is 16. So if I take 16 and I square it, I get 256. Measured in centimeters squared, of course. Now, let's talk about these small triangles. Because the small triangles, there are 4 of them, and each of them has a right angle. So we've got a right angle there. And then we know that if this whole side is 16 centimeters, then half of it is 8. Okay. I also know that this side over here is 8. Well, because we have 2 sides that are the same, that means we have an isosceles triangle. And by the isosceles triangle theorem, that means that the opposite angles must also be congruent. If the sides are congruent, then the opposite angles must also be congruent. That makes this a 45, 45, 90 degree triangle. And that is a special right triangle. So, if this is a leg L, and this is a leg L, then the hypotenuse should be L square roots of 2. So now I have all of the sides. And now that I think about it, we really don't even need all of those sides. So I guess technically I should erase this from the video and go back and kind of redo this section, but I kind of like where this is going because in my mind I was thinking I need all of the side lengths. But think about the area of a triangle. What's the formula? 1/2 base times height, right? So look at your triangle. The base doesn't have to be the big part, and the height doesn't have to be right here. I can have a base here and a height here as long as they're at a right angle to each other. So I can just use what's provided for me, that the base is 8 centimeters and the height is 8 centimeters. So rather than take this out of the video, I kind of like that this was in here. So when I multiply all of those together, half of 8 is 4, and 4 times 8 is 32. Now, how many 32 centimeter squared triangles are there? Well, there's 4 of them. 1, 2, 3, 4. So if I take 32 and I multiply by 4, that's 128 for the total area for those triangles. So in order to find the area of the shaded square, I want to take 256, the big square's area, and I want to subtract from it all 4 triangles, 128. So if I subtract, my area of the composite figure is exactly 128 centimeters squared. Interesting problem. Okay, let's go on to part D. Part D says, find the area of the composite figure. Now there are no shaded sections here, so I'm going to assume that the entire figure is the composite figure that I need to be finding the area of. So what basic figures can we break this into? Well, I notice this little piece right here, so that's a semicircle. And then this right here, one of the lengths is 17 feet, and this down here is 20 feet. So that means that this must be a trapezoid, and I have the height right here. So let's think about formulas. For a semicircle, the area of a circle is, pi r squared. But if I only want a semicircle, then I need to divide it by 2. And for a trapezoid, the area of a trapezoid is 1/2 times the sum of the bases, base 1 plus base 2, times the height. So we have all the pieces that we need. Let's find the area of the semicircle first. Pi times the radius. Well, if the diameter is 17, how do you find the radius? The radius equals half of the diameter, so 17 halves. Over 2. Okay. So the area equals pi times 17 squared, which is 289, over 2 squared, which is 4. And you're dividing it by 2, so you're multiplying by another 1/2. So 289 divided by what is really 8 does not get simplified. So I can say this is 289 pi over 8. So now let's look at the trapezoid. The area of the trapezoid is 1/2 times the sum of the bases, so base 1 is 20 and base 2 is 17. So 20 plus 17 is 37, times the height. The height is 13 feet. So my area of the trapezoid, I can't take 1/2 of 37 or 13 in a nice way, so I'm going to multiply 37 times 13. That's 481, and I'm just going to put it over 2. This is measured in feet squared. This is measured in feet squared. So I'm going to add, because my composite figure is everything. So my area of the full composite figure is 289 pi over 8 plus 481 over 2. And I can leave this as the sum and then feet squared, or I could also create a common denominator, make this an 8 by multiplying by 4, multiply this by 4 as well, and then just have 289 pi plus 481 times 4 over 8, and that would be acceptable as well. Okay. Last problem, part E. I need to find the area of the shaded region. What basic figures can we break this into? Now, I'd like for you to pause your video, and I want you to break this into the 2 basic figures and write the formula for the area of them. So that's what you need to do once you pause your video. and then come back for the rest of the problem. So write the two figures that you can break this into and write the area formulas for them. Pause your video. So hopefully you saw this large rectangle here, and then this little semicircle that's kind of cutting into it. So in this situation, we're finding the area of the shaded region, which is the area of that rectangle, and then we need to subtract out that blank space, that area of the semicircle. So the rectangle formula for the area is base times height, and then the semicircle is the area of a circle divided by 2. So what I'd like for you to do is pause your video, calculate the areas for each of these separate figures, and then combine them in a way with addition or subtraction that will give you the area of that shaded region. Pause your video and find the area of the shaded region. So you should have calculated that the area of the rectangle is 1,500 feet squared, and the area of the semicircle is 225 pi halves feet squared. To get the area of the shaded region, you want to subtract. So the area is 1,500 feet minus 225 pi halves feet squared. Now you can leave it like this, but I'm going to do what I mentioned on the last one. I'm going to go ahead and create a common denominator. So I'd like this to both be over 2. So this is 3,000 over 2. So I can create a common denominator of 2, and my numerator would be 3,000 minus 225 pi feet squared. So this is acceptable as well. So our last question today is kind of a reflection question. So why was it that we subtracted on some and added on others? Is there a way that I can determine when to do what? So why did we subtract on the ones that we subtracted? Well, we subtracted on part 1b, and we subtracted on 1c, and we also subtracted on 1e. So we subtracted on all of these. Why did we subtract instead of add? Well, the whole figure wasn't shaded. There was shaded sections, and then there were pieces that were taken out. So we subtract. When pieces are shaded and some are not. So that's the way that you can determine when to do what. If there are pieces that are shaded and non-shaded, then that tells you you're probably going to need to subtract. If everything is shaded, or if everything is not shaded, if it's all the same color, then that means you're probably going to add.